This is problem 1 from the fall 2010 exam. It says a jeweler needs to electroplate gold onto a bracelet using an ionic solution. He knows that the charge carriers in the solution are gold ions of charge plus E, and that gold ion has a mass of 3.27 times 10 to the minus 22 grams. The gold ions move through the solution, deposit on the bracelet. He's calculated that he must deposit 0.2 grams of gold to reach the necessary thickness. If each gold ion has a mass of 3.27 times 10 to the minus 22 grams, what current should he use to electroplate the bracelet in 3 hours? Okay, so he's just going to run a current through this metal bracelet, and then gold ions are going to deposit themselves on the surface. And he needs 0.2 grams of gold. So we need 0.2 grams of gold, and each gram is 3.27 times 10 to the minus 22 grams per atom. So this is some number of atoms that he needs deposited onto the bracelet. So this is some number of charges in some amount of time, which is the current he needs. So the answer will be current is charge per time. The charge is this answer right here, so 0.2 grams times the number of, we do grams per charge effectively also. So 10 to the minus 22 grams. So this is the number of charges, and the amount of time is 3 hours times 60 minutes per hour times 60 seconds per minute. So this will give us something in charge per second, which will be our current. And if you do this, you will get 9.1 milliamps for this answer. So this is A. Part 2. The figure shows an electric field vector as a function of position. The figure shows that the electric field strength decreases continuously when moving left to right. Which set of equipotential surfaces matches this electric field distribution? So we have over here on the right side a small electric field, and then as we move to the left we have a large electric field pointing in this direction. So this represents the strength of the force on a single positive charge. So if we're over here, if we put a positive charge over here, we'd have a small force on it. If we put it over here, we'd have a large force on it. So it's kind of like we have a big blob of negative charge right here. So if it's close to the charge, it experiences a large force. If it's far away from the charge, it experiences a small force toward it. And so we're supposed to pick which equipotential surface diagram would match this charge distribution. And so if you look at the choices, the equipotential surfaces have to get closer together over here where the field is large, and then farther apart out here when the field is small. So that would correspond to either C or D. And so the difference between C and D is that one of them has a high potential over here, so it says 50 volts and 0 volts, and then D has the opposite, so it says 50 volts over here and 0 volts over here. And we know that a positive charge will go from a high to a low potential. So we know that it has to have a high potential over here and a low potential over here, which corresponds to C. And so the way to think about this also is that the equipotential surfaces are like if you had this big hill that this charge was on. And so it starts off kind of not so steep over here, and then becomes very steep over here. And so your positive charge would experience just a small force in this direction when it's over here, and it would experience a very large force in that direction when it's on this part of the hill. And these equipotential surfaces just mark a change in height. So a constant change in height of this hill. And you can see if you were looking at it from the top, then it would look like these points were all very close together, and then as you look up here, as the slope is very small, they would spread out. So that's the reasoning behind choosing C. Okay, part 3. Shown is a ring in the XY plane with half uniformly distributed positive charge and half uniformly distributed negative charge. what best describes the electric field E and the electric potential V relative to infinity at the center of the ring? So circle 2 answers, one from each column. Okay, so we have split along some direction. We have a positive charge on one side and a negative charge on the other. So if you imagine putting a positive test charge here, then it will be attracted toward all of this charge that's here and repelled from all of this charge. All of the components along this axis along the y-axis will cancel out, so you always have an equal amount of positive charge over here that's going to push it this way, as you do amount of positive charge over here that will push it back this way. So the net force from all this positive charge will have to be in this direction, and the net force of all this negative charge will have to be in this direction, so the net force will have to be along the negative x direction. So that'll mean B. And let's see, the electric potential, the way to think about this is that the electric potential of a single charge somewhere on this ring is this is the potential due to a single charge, is K times the charge divided by the radius. And so all of these charges are all at the same distance. And in this case, we just have some amount of, this is a linear charge density that's spread across this whole part of the ring here. So the potential due to the positive charges is something like K times, this is lambda positive, the positive charge density, times the amount of ring that you have. And this is divided by the radius of the ring. And then due to the negative charge is this. And so if these positive and negative charges are just equal and opposite, then these will cancel. If you had, so the potential will be 0 there at the center of the ring. If you had different amounts of charge density on either side, you would do this in the same way, except for these two terms wouldn't cancel. Okay, so number 4, in this circuit, what is the current leaving the battery? Okay, so what we have to do to solve a problem like this is take this kind of complicated resistive circuit and make it into something simpler. So we want to make it into some sort of circuit like this, where this is some R effective and this is your battery still. And then we can just use Ohm's law and say that the voltage is the voltage of the battery. This is the R effective, and then we'll solve for the total current in the circuit, and that's the current leaving the battery. So to do that, we have to collapse this circuit down into some simpler R effective. So the way to do that is look here and say, well, these two resistors are in parallel, so we can combine these two resistors into one effective resistance. And we pick these two because these are the only ones where we can say, right now at least, for sure that the current must either go through this one or through this one. And there aren't any other paths. So this is 200 ohms and 200 ohms in parallel, which will be 100 ohms. So two equal resistances in parallel will come out, have an effective resistance of 1/2 either one. So the equivalent circuit of this is we have our battery. Oops, here was 200 ohm. Here is 100 ohm. And then we have this parallel resistance here, which was effectively 100 ohm. So now we have this circuit, which we collapse down and say, okay, well, these two resistors are now in series, so they just add. And so from this, we get a circuit where here's our battery, here's this 200 ohm resistor here, and now these 200 ohm resistances combine and make a 200 ohm resistor. And then now we can combine these two resistances in parallel as an effective resistance of 100 ohms. So this is our effective for this whole circuit. So now we have 10 volts, a 10 volt battery, and 100 ohm effective resistance. So the current, like from Ohm's law, is V over R, which is 10 volts divided by 100 ohms, which is 1/10 of an amp.